All right, you might be wondering what was the point of getting a relationship for the magnetic moment? And one way to see that is that this corresponds to a potential energy if a magnetic field is applied. And you might remember this relationship from your electromagnetics last semester. But we have this potential energy UB, which is equal to the negative of the vectors of mu dot B. And if we're now looking at a magnetic field that is applied along the z direction, as actually shown in this diagram here, where we have this B vector going along the z direction, then we already got the mu z, so we can just write that in here as this ml quantum number times mu b. Okay, so this potential energy when the magnetic field is applied is in additional to that total energy that we saw from the Bohr model or from that boundary condition for the radial dependence. So in other words, this 13.6 eV for the ground state energy. And what this means is that you can have a splitting of the energy levels when you make a transition. So shown in the bottom diagram is the case when you're going from an L equals 1 to L equals 0. And this is when no magnetic field is applied. And so what that's saying is that you just see that energy of the photon, and here F is the frequency, so you could think of that as nu. And so this is the frequency that you expect from the Bohr model, or from a case where you're not worried about the ML values. However, and in fact that's always true when there is no magnetic field applied, but once you apply the magnetic field, then this extra potential energy term, UB, is either added or subtracted depending on the sign of M. So you see that M could be -1, 0, or 1, and then you're either adding or subtracting that relatively smaller amount of energy, which is splitting that energy level into 3. And then you can have a transition down to the lower ground state, and because that upper level is split in 3, you get 3 different energies of photons coming out. And this was measured back in 1896 by Peter Zeeman, and it is now known as the Zeeman effect. This is a simplified version. It can be a lot more complicated depending on a fourth quantum number, which we're going to talk about next. And that is the spin angular momentum. Now this is interesting because this does not come from the solutions to the Schrodinger equation for the hydrogen atom. In fact, it comes from the relativistic effects of the electron, and an equation that's beyond the scope of this module, and you will probably get to when you deal with particle physics, is the Dirac equation, where Dirac included relativistic mechanics with the quantum mechanics to get what's known as the Dirac equation. And in that, this concept came out. But it was already predicted as by Wolfgang Pauli and Goldschmidt and Uhlenbeck in 1925 to make sense of some of these emission lines that we're seeing from hydrogen. So this quantum number is known as a spin, and we have a diagram shown on the bottom where we have this electron, and the idea is that it acts as a spinning angular momentum, that this electron is spinning around its axis, and that creates its own angular momentum. So this is, instead of capital L, we're calling it S to say that it's a angular momentum caused by spin, and we have that the magnitude of S vector is the square root of little s times s plus 1, and that's all multiplied by h bar. Notice that this follows the exact same way that we included the quantum number, which now is little s, as for what we had done with the orbital angular momentum. The interesting thing, though, is that s can only have one value, which is 1/2 for the electron. Now we can also, similar to what we did for the orbital angular momentum, we have a z component, and that looks very similar, where you have m times h bar, but notice the subscript s. This is telling us that this is a this is now only related to the spin, and ms is equal to minus 1/2 or 1/2. And actually, this is normally what people think about for the quantum number, the spin magnetic quantum number. Little s is usually not considered, but that's just because it can only have one value. Whereas with ms, you have either a negative or a positive 1/2. And if we go back to the diagram, that corresponds to this case that's known as spin up or spin down, depending on the orientation in the positive or negative of that